Hi everyone, so we're going to be doing mass spectra. Now this part is HL only, so if you're doing SL, this is not for you, you can skip it, you can move to the next video. So you're supposed to know how to use the mass spectrum to determine relative atomic masses of elements from their isotopic composition. And you're supposed to interpret the mass spectra to identify the isotopes and to know how much of the isotopes that you have. So a mass spectrometer is an instrument that is used to determine the abundance of the various isotopes of an element. So if you look at a mass spectrum here, it will tell you that there is an isotope of mass 35 and of percentage 75%, like this. So you get the isotope present and you get the percentage abundance of that particular isotope. Now you have a mass to charge ratio. The mass to charge ratio, this is what gives you the AR of the isotope, which is the isotopic mass. Let's see the process to understand better. So the sample is vaporized first, so it's going to turn into a gas. Let's say we start with chlorine, a sample of chlorine. So you're going to first vaporize. It turns into chlorine gas. Then you're going to ionize a sample. Ionize means turning into ions. We're going to turn it into positive ions, singly charged, so +1 ions. So if you have chlorine 35, it's going to become chlorine 35 plus. You have chlorine 37, it becomes chlorine 37 plus. So you have those ionized particles now. Then the positive ions are accelerated in an electric field, and then it's going to be passed through a magnetic field in stage 4. In the magnetic field, the particles are going to be deflected. The one that is lightest is deflected the most. The one that is heaviest is deflected less. So then chlorine 35 here plus is going to be deflected more than chlorine 37 plus here. So then you have a detector that is going to find out how much of chlorine 35 there is and how much of chlorine 37 plus there is. So it gives 2 peaks. So each peak corresponds to positively charged ion peaks. So this gives 1 peak, this gives 1 peak. The height of the peaks depend on the composition. So this is obtained at 75%, and then this one is obtained at 25%. So the height of the peak corresponds to the percentage composition, how much there is. And on the x-axis, you have relative isotopic mass, which is given as m/z values. The m/z values is mass over charge ratio. Now, what is the charge? If you look here, the sample is ionized. It's turned into +1 ions. So then the charge is +1, which means that the mass is going to be simply the isotopic mass. So when you see 35, this corresponds to chlorine 35 plus. When you see 37, it's chlorine 37 plus. How do I know it's chlorine? Because it's given, normally it will be given in the question which element we are referring to. So a mass spectrometer separates the individual isotopes in a sample and determines the mass of each isotope. So it's the isotopic mass. So information that we can get from a mass spectrum, the number of peaks indicates the number of isotopes. So you have 2 peaks here, so there is 2 isotopes. Then the position of each peak in the horizontal axis indicates the relative isotopic mass. It's referring to this, the position of each peak on the x-axis. And the relative height of the peaks correspond to the relative abundance. So you can see the percentage abundance here. And these are the three pieces of information that you can deduce from this mass spectrum. Now, on a mass spectrum, you do not only get isotopes, you will get other fragments also. So you can have individual ions, you can have the whole of molecule, which is called the molecular ion peak. You can have fragments of molecule, but everything that is detected on the mass spectrum will have a charge of +1. So the m/z value is used to determine the mass of the species. Now, when we are looking at, let's say, the mass spectrum of chlorine. Now, chlorine, you know, chlorine gas exists as Cl2. So it's chlorine molecules. So then in the mass spectrum, you will get chlorine ions, the individual ion, but you will also get the peak of chlorine molecule. This is what it means here. You can get individual ions, you can get whole molecules also. There's no fragment here, but if you have mass spectrum of, let's say, CH4, you can get H+, you can get CH3+ also. This is a fragment of the molecule. So, coming back to the case of chlorine molecule, the chlorine ions will give you chlorine 35+, chlorine 37+. These are the two ions, and you see it here. So this gives 75%, this gives 25%. But you will also get chlorine molecule. Now the chlorine molecule can be made up of chlorine 35 and chlorine 35. It could be made up of chlorine 35 and chlorine 37. It could also be made of chlorine 37 and chlorine 37 that combine together. When these combine, the m/z value here would be 70, which shows up as a peak here. For this particular molecule, the m/z value would be 72, and for this one, it would be 74. So these ones here are molecular ion peaks. Molecular ion peaks. And the molecular ion peaks are usually at the end of the spectrum. It's the one with the highest m/z values. Now, if I need the average relative atomic mass, the average, I would do the average of these isotopic masses. If I need relative molecular mass, I will need to average these molecular ion peaks. All right. Let's look at the first example. So here you have the mass spectrum of magnesium, and you need to find the relative atomic mass. So relative atomic mass is found from isotopic masses. So you have magnesium 24, magnesium 25, and magnesium 26. If any question asks you what species is responsible for this peak, please do not say magnesium 24. That's not the species responsible for this peak. The species is Mg24+. It has to be positively charged, because remember that in the process, the sample is ionized, so it has a +1 charge. So all of these peaks have a +1 charge. So this is responsible for this peak. Mg25 plus is responsible for this peak. Mg26 plus is responsible for this peak. The functioning of the mass spectrum is not required. Operational details is not going to be assessed. But you need to know to understand how do we get Mg plus, why it's this percentage, etc. So to find the atomic mass, I will proceed in the same way as we did previously. So it's percentage times relative isotopic mass. Sum of percentage, so 10 times isotopic mass. And then when you are using mass spectrum specially, you have to check the sum of the percentages. It might not necessarily add up to 100%. You have to be very careful. In this case, it adds up to 100, so I will put 100. In some questions that you're going to work out, past papers questions, you will find that they do not add up to 100%. So this is the answer that you get. Next one. Now for this one, if you want, you can pause the video, do the question, and come and check your answer. Now, the relative abundance is not going to always be given. In this case here, it's percentage. In this case, it's relative intensity. So you're not going to get things to add up to 100. So in that situation, that's why I mentioned that be careful, check the sum before you work. So estimate the relative abundance of each isotope. So you are estimating. In the marking scheme, normally there's going to be a range that is going to be valid. So let's estimate. So this one, here is 0.5 approximately, so this would be 0.25 and so on. Your values might be slightly different as mine. I'm not using a ruler. If you're using a ruler, it might be slightly different. And then use your estimates to calculate relative atomic mass. So you can see here that when I add these relative intensities, it will not add up to 100%. So then when you're calculating the relative atomic mass, then you will use the AR value, so 204 times 0.25, and I'm going to work for each one. And then my denominator, the one at the bottom, is going to be a sum of the relative abundances. So this is the answer. Now, if you look at the values here, this is free SF. All of these are free SF. Free SF. This is 2SF. Minimum SF is 2SF. So when you give your answer should be to the minimum SF or one better. So answer should be either 2SF or free SF. So I'm going to leave my answer as free SF. So 207. And that's it. And the last question, you can work this out, pause the video, and then you come back for the answers. So this is my answers. So for nickel, you see you have 4 isotopes. These two, you might miss them. They are very small. So there's 4 isotopes. I've approximated the values. If your relative intensity is slightly different, that's fine. And this is my isotopic mass for nickel. For AR, there is only one line, only one isotope. So it's only 59. So deduce which one has a larger AR. So it is cobalt. Now the actual value of AR for nickel is 58.69. The value is slightly different. Why? There's 2 reasons why it's different. The first one is that all these values that you used here, the relative intensities, these are approximate values here. We've guessed it from the spectrum. It's not the real values. So this might affect this answer. And the second reason is that no one says that there's only 4 isotopes. There could be more isotopes. So maybe other isotopes are present. So you can have those 2 reasons. So this will end with S1.2. There's the homework. You complete the homework for this section.